Hello everyone, welcome to this session, welcome to this channel. I'm Saptarshi Mukherjee, I'm a software engineer 3 at Google and I'm a competitive programmer. So in this particular session, I'll be discussing the first 4 problems of yesterday's Codeforces round 934. It took place in Div 2 as well as Div 1. I participated in Div 1 and I'll be discussing the first 4 problems of Div 2, which includes 2 problems from Div 1. So um, a quick look at how my contest went. The first problem, I actually committed a mistake at around 11 minutes 51 seconds, and then it took me around 4 to 5 minutes to correct it. So at 16 minutes 41 seconds, I had my first correct submission. Thereafter, this problem was actually a very good one. I had almost solved it around 1 hour 6 minutes 47 seconds. But then there was a small issue, a small -1 kind of issue, to rectify which it took me around 47 minutes. I actually got distracted towards some other things that I thought as mistakes, and that is the reason I actually took extra 47 minutes. So yeah, overall this sort of had some rating difference of -15 on me. That was my rating change post the contest, but I hope, I believe that, yeah, if I would have done it quicker than these 47 minutes, this rectification of that small error, had it happened quicker, I would have saved my rating. Maybe my rating would have increased. But anyway, these things happen. But it was a good learning or a good experience for me in Div 1. So let me walk you through the 4 problems. First 2 problems from Div 2 and these 2 problems from Div 1. I had some submissions in D1 as well. If you go to my submissions, you will see I had some submissions, but they definitely were not prepared. They faced the wrong answer verdict. I think this is solvable. At the end, I can share some ideas, or maybe we can discuss it separately. And see, from the constraints, I believe there is not going to be a simple diameter kind of a thing. We can quickly look at them, but basically most of this will be centered around the first 4 problems of Div 2. And the first 2 problems I have not solved. So while explaining, I'll actually code it down and submit it, and I'll show that whether it works or not. See, I've myself not seen whether those approaches work or not. So I'll myself code and show you whether it works or not, and see myself as well. And these C and D, definitely, I'll share the insights and then I will show how I solved it. Okay, so let us see. Let us look at the first question. Destroying bridges. N islands are there, and every pair of islands is connected by a bridge. So this is a graph question, and in the graph, if every node is connected to every other node, you have nc2 number of bridges, number of edges. So you have n into n minus 1 by 2, these many edges in the graph. Now, some guy is on island 1, and they enjoy visiting other islands using bridges. Dominator has the power to destroy at most k bridges to minimize the number of islands that this guy can reach using possibly multiple bridges. So at the beginning, this Dominator can destroy at most k bridges. We have to say which ones they will destroy, or after they optimally destroy, what is the minimum number of islands that Evrul might get to visit. Which means that if the Dominator is not very diplomatic, not doesn't have a good strategy of destroying, then probably even after destruction of some bridges, Evrul can go to every other island. We don't want that. We want the maximum possible impact of the destruction. What is that maximum possible impact? That many islands cannot be visited. So we have to tell, after that destruction, what is the minimum possible number of islands that they can visit, that Evrul might be able to visit. So let us see how this problem looks like from the graph point of view. Problem, actually the solution I think was easy, but how the solution came, etc., needs a bit of thinking. So let me try to shed light. Let's say you have n equal to let's say n different nodes, 1 2 3 4 5, whatever, you have these nodes. Now the moment we are saying that they are starting on node 1, and they should not be able to visit some other nodes, some node x plus 1, maybe the node n. We are saying, let's say, that these nodes they cannot visit. And basically what this means is that there is no edge. Let's say these nodes they are able to visit, so there exists some sequence of edges between them. Maybe all possible sequence of edges are there, and there is another one, probably you have all possible sequences of edges between them, or maybe lesser. And but from the left to the right there is no possibility. There may be some other parts over here, right? This is what a disconnected graph basically means. So if you are not able to visit from one to a particular node X, that means there is no such path going from anything in the left to this X. There should be nothing like that. So when we say we are not able to visit few nodes like X, X plus 1, N, that means they are all totally disconnected from these nodes which can be visited, which are in the area that can be visited. So how can we disconnect it? These are the possibilities: that you keep one node which anyway is visited, and from that disconnect everything else. So everything else, this is the best possible thing, this is the minimum possible thing. So you can say, okay, else every kind of node is present over here. So in that case, how many edges do we have to destroy? From this node, whatever edges are going there, we have to destroy them. So from 1, it will be an edge to every other node. If it can go to any of them, then this particular setup is not possible. What we are basically saying is that only one node can be visited, nothing else can be visited. Everything else is over there. I mean, in the not visited, but we are making a partition over here. So there's a graph partition. So that means these edges won't be there. These edges won't be there. So how many edges do we have to destroy? These many edges, which is n minus 1. N minus 1 needs to be destroyed. Now, if I say that, okay, if I will allow two nodes to be here in the left, two nodes that can be visited, one of them of course is 1, and other nodes cannot be visited. So all the other nodes are here, n minus 2 nodes. There are n minus 2 nodes present over here. Then basically what we are saying is, there is nothing going from left to right. There is nothing going from left to right. These things won't be there. And hence, how many such edges are there going from two nodes to every other node? That is 2 into n minus 2. Okay, there should be no edge going from the left to the right. So if I say that, okay, two nodes I'm going to protect, everything else over there, then these many edges needs to be destroyed. And similarly for any I, if I want that the, let's say, first I nodes should be, that should be able to be visited, the others should not be visited, then it basically comes to I into n minus I. These many I have to visit. Now if we compare them, this basically means something like 1 into n minus 1. If you compare them, n minus 1, 2 into n minus 2, 3 into n minus 3, 4 into n minus 4, and so on. At the end you will have, something like I into n minus I. If you take some example, let's say n equal to 10, what do you see? 10 minus 1, 9, then 2 into 8, 16, then 3 into 7, 21, then 4 into 6, 24, and so on. Can you see it is rising? It is increasing. Number of required nodes is increasing, which means it is easiest to make this kind of a split. That one node stays here, everything else stays in the right. Right? So, the summary is that if we have to disconnect a graph into two different components, a fully connected graph, so initially what we are given is a fully connected graph. If we have to convert a fully complete graph, which is referred to as CN in your graph terminology, if you have to convert it into two connected components or two different components, then the easiest way is, then the least number of edges to be destroyed. In that sense, the easiest ways 1 versus n minus 1. When I say easiest, what I basically mean is least number of edges to be destroyed. Which essentially means that, okay, if you destroy n minus 1 edges, then the number of nodes that ever rule can visit is only 1. Number of nodes that can be visited, which you are happy with because you have to minimize. Anyway, you have to minimize. So that 1 is fine. Now, if if you have greater than equal to, if the destroying power, if the destroying capability is greater than equal to n minus 1, if that k is greater than equal to n minus 1, then you can restrict everyone to visiting only one node, that is the first node. However, if it is less than n minus 1, that means no such separation is possible. Always there will be a link between the two components you are trying to divide them into. It is never possible to isolate nodes. So if I take one example of, let's say, n equal to 4, for n equal to 4 you have something like this. This will be your complete graph. So I have formed these 4 edges. Now what I'm saying is, if you have n minus 1 capability, then if you have k equal to n minus 1, you can break this one, and this one. Let's say this is 1. You have broken those 3 edges. Now from node 1 you cannot go to any other node. From there you cannot go anywhere. So if you have n minus 1, then fine, you're winning. If you don't have n minus 1, let's say you have less than that. So n minus 1 is 3. So if you have, when n is 4, here n is 4. So if n is less than 3, let's say it has only 2. Then which 2? You separate any 2. Let's say this one and this one. You might think you will not be able to reach here, but you have so many other ways to reach here. This way, that way. So yeah. So that means if it is less than n minus 1, then unfortunately you cannot disconnect anything. So the nodes visited will remain n. You're not able to isolate anything. So yeah, that's it. That means this is the only thing you need to check. Whether your k is greater than equal to n minus 1 or less than n minus 1. So I don't know. Probably many people would solve this question, which is not a wrong thing to do. Probably many people would solve this question without thinking so much deeply. But yeah, if you have to understand why it works, then this is the reason. Okay, let me solve it now. T, n and k, and I'll just write it in one line. Println, basically say, okay, if k is greater than equal to n minus 1, then yes, no, okay, no, then basically if it is greater than 1 and if it is lesser than n, right? And I hope the ordering is correct. Sorry. So 214151, let's see. Okay, it's a bit confused. Fine. 214151, let me see if this works. Okay, Codeforces queue. Yeah, it's accepted. So this was correct. Okay, now next question, let us look at equals or. A very interesting question. It says that you have an array of length 2n and each integer from 1 to n occurs exactly twice. Nothing can be easier than this. So it has given as much detail as you needed for this question, maybe much more than that. It basically says that each integer from 1 to n, it tells you what integers are there, it tells you the frequency. Just the ordering is not told, that's it. Which element is present where, that is not told. Otherwise, what is present, how many elements, how many frequency, etc., everything is there. Then you're given some k, which is up to n by 2. Now you have to find two arrays L and R, each of length 2k, such that L is a subset of the left half of array A, R is a subset of the right half of array A, and the bitwise XOR of the elements of the left half subset is equal to the bitwise XOR of the elements of the right half subset. So there are two subsets you are creating. First subset must come from the left half, second subset must come from the second half, right half, and the two subsets should basically give you the same value of bitwise XOR. The value can be anything, it may or may not be 0. So let us take some example and see if we can form 6 for, let us take this one, 642123 163554. 642123 163554. 163554. This is that dividing line. So your left half will come from here, L, and your right half will come from here, R. And the K given is 1. We can pick up some other K as well. We can pick up, let's say, K equal to 2 so that we understand better. So that means you will pick up 2 elements from the left half, 2 elements from the right half. Let's first pick up K equal to 1. So if I pick K equal to 1, I can say, okay, 1 element. We can pick up this 6 from here, 6 from here. So for K equal to 1, your L will look like 6 and R will also look like 6. Same thing. For K equal to 2, let's say if I do K equal to 2, then is it possible? Yes. So I can pick up something like this, 6 and 1 and 1 and 6. These are not the only answer, so maybe let's put down what possible answers we have. 6, 2, and over there also I can put 6, 1, 6, 1, and over there I can put 1, 6. Fine. If I put 6, 2, it will become slightly funny. 6, 2 and 5, 1 probably would give me the right answer, but it might be complicated to figure out those cases. What else? I can say, okay, these 2 and this 5, 5, 5, 2, 2. So 2, 2, 5, 5. These are two possible answers. There are possible other answers as well. Now, how to reach two different arrays L and R such that their XORs are same. For this, the biggest hint is actually given, that each element occurs twice. So the elements are in this range 1 to n. Now when I look back at this particular condition that is given in the question, I mean the information that is given in the question, I don't really need this information. This is an extra information for me. This will help in my implementation. So my implementation I can make in such a way that it works for this only, because that is easier to implement. But the most important thing is each element or AI occurs twice in the array. Occurs twice, exactly twice in the array. From 1 to n, each element occurs twice in the array. This is a big information for me. This is a big information for me. Okay. Now, each of length 2k. Okay, I think for k equals to 1 also they needed something like that. 2 elements in the left, 2 elements in the right. So I beg your pardon, if k is 1, then this particular answer is actually allowed. K equal to 1 means 2k length for the left L and 2k for the right L. So this is for k equal to 1. Now, how can we solve this? What information do we get from here? If an element occurs twice in the array, what are the possibilities? Let's say that element is x. That means there are two different x. There are two x present in the array. What are my possibilities? One is both in left half. Another is both in right half. Another is one in left half, one in right half. Correct? For a certain element, an element is present twice, so it can be present both times in the left half, both times in the right half, or one in left half, one in right half. and 1 in right. And there is absolutely no information telling me which one it is. It can be anything. It can be any one of these. So, if it is the last one, can I say we can pick up those elements in our XOR? Because if I know that, okay, let's say x equal to 1, 1 is present in the left also, 1 is present in the right also, 2 is present in the left also, 2 is present in the right also. If I have to pick up only 2 elements from left, 2 elements from the right, can I say I can pick up this 1 and 2? So 1 XOR 2 and 1 XOR 2 from both the ends will give me the same XOR. So I can pick up those elements which are occurring both in the left and the right. Right? We can pick from both. We can simply pick from both. Now, what else? Now, if that is not sufficient, you have to pick up 2k. So from the left you are picking up, from the right also you are picking up same elements. If that is not sufficient, what else? What other ways do you have? From these two things, what information do you get? Let's say some y is present. Some y is present in the left. Some y is present in the left. Some z is present in the only in the right. Then what kind of situation do we have? In the left we have y. In the right half we have z. So can I say, okay, pick two y's in the left and two z's in the right? How will that help me? I know that y XOR y has no impact on the answer, on the XOR, because y XOR y basically is 0, 0 XOR anything is that anything, which means I will take both the y's here, both the z's over there. The easiest thing possible in XOR, the most interesting thing possible in XOR, which means given any kind of situation, let's say this situation, if I have to, let's say, solve this for k equal to 3, what can be one of my strategies? Here of course, I mean, k equal to 3 means take everything. So if I say, okay, for k equal to 2 only, what can be my strategy? I can say, okay, what is common between the two? 1 is common, lying both on left and right. 6 is common, and then 3 is common. So one easy option is take this. Okay, another one is needed, so 4 is common. 4 is common. So I can say, okay, keep on taking them. So you have 6 XOR 4 XOR 1 XOR 3, and over there you have 1 XOR 6 XOR 3 XOR 4. Both will be equal to the same thing because they are the same elements, right? And then if something is left, you can take this in pairs. You can take this in, now the remaining things must be located in pairs. You don't fear that now they'll be located in odd numbers or something like that. Now they will be located in pairs. These numbers will be in pairs. Can we say that? 3, let me see, 6. So you have how many numbers? You have 12. 6. Okay, can it be 5? Can n be? Yes, n can be 5. I mean, n can be an odd number, right? N can be an odd number. So there is that small thing you need to be careful about. What is that? There is a small thing. Let's say you have only 5. Let's say n equal to 5 now. So you have something like this, 3, 3, and then 1, 2, 4, and then same thing over here, 1, 5, 5, 2, 4, or 4, 2, or whatever arrangement. Now if your k is equal to 2, let's say, so you have to pick up again 4 elements. Here if you first pick up these single elements, there is a problem. You enter this problem. So if you pick up 1 to 4, then you enter basically this problem, that now what will you pick up? You have picked up 1, 2, 4 from both of them. Now what do you pick up? There's a big problem. Why? Because now basically both are in pairs. If you pick up 3 from here and if you pick up 5 from here, that will not solve your problem. If you pick up both the 3s and both the 5s, then only the XOR will come out to be the same. But if you pick up 1, 3 and 1, 5, that will not solve your problem. The XOR will be different. So then you have to say, okay, don't take one of them, take one of these. So don't take this one, take one of these. Sorry, both of these. So those things, those elements which are in these first two categories, categories A and B, then you have to take in pairs only. I mean, from each half you have to take them in pairs only. So here I'm basically relaxing something from category C to take from category A. So first picking first from category C is a problem. Picking first from category C is a problem. Yeah, because it may leave only even elements when you need odd number of elements, only even pairs while you need odd elements. So a better approach is, now another important thing, will A and B be of the same size or different? If you think a bit, you will say, okay, C has the same contribution to left and right. A has only contribution in the left, B has only contribution in the right. So we can say the size of A is equal to size of B. Size of A, that is the first category, is equal to size of B. So strategy can be, okay, A and B we will do first, and after that we will go to C. This can be the sequence, right? So first A and B, that is which occurs only in the left, and then C which occurs only in the right. That's it. That way we can solve it. So let us maybe solve it. So I hope the screen is visible. Okay, NK and then AIs. NK, I'll take the inputs. For I equals 0, I less than I plus plus, and then AI is equal to sc.nextInt, and then I'll instantly maybe store in a hash set, or I can do it separately. That hash set integer set1 equals to new hash set. I'll keep set2 and set3. Okay, next I'll say that for I equal 0, sorry, I equal to 0, I less than up to n. So we are taking up to 2n. This is important. 2 into n. And now I'll say that, okay, go only up to n and put everything in set1. So set1 dot add AI. Similarly, I will say that for the second half, add that in set2. For the second half, that is from n to 2 into n, we'll put in set2. And next, I can say in this way, from 1 up to n, whatever lies in both set1 and set2, then we will put in set3. If set1 dot contains I and set2 also contains I, then I'll add this in set3 dot add I. Next, one thing more I can do over here is I can remove it from set1 and set2 if it allows me. Let me try dot remove I, set2 dot remove. Then it will just remember what is unique to the left and right. So set1 stores only the unique in the left, set2 stores only the ones which are unique in the right, set3 stores which are common in both of them. And I'll say, okay, now which one did we plan to prioritize? the a slash b, which is only in the left or only in the right that part. So we can just take keep on taking that. You have to take in pairs. So so we can say int car. Currently we have taken 0 and we have to take 2k up to each. So while car plus 2 is less than equal to k, and or we can do something different. Uh, Instead of that thing, we can store in an array as well some of this information. So array, what way can it be possible? Array list integer. I'll store the left half. So left equals to new array list, and the right over here, and then I'll say okay, for I equals to 1, I less than equal to n, I plus plus, if my set to 1 dot contains I, we could have done it that way as well. There would be a problem actually. So let us do it this way only. Yeah, let us do it the way we actually don't need, I think. Let's but this will make it easier. So if set1 contains I, then left dot add I. If set2 contains I, right dot add I. Okay, now we will take while uh, car is greater than equal to 2. Okay, then we will do this. We will say take something from the left, take something else from the right. So for that I can keep something as y, and then I'll say okay, the left. Now our answer for that, I'll again need some things. So let's say a left and a right. That is the answer to the left, answer to the right. So a left dot add left dot get y another time, and the right will get it again the same way. So a right dot add right dot get y. So when you implement, you actually know why it is slightly harder than as the logic actually seemed like. Y plus plus. Okay, car greater than equal to 2, so car minus equals to 2. This is how this part will be. Now whatever card is left, while car, okay, another thing, and y is less than left dot size. We know left dot size and right dot size are the same thing, so this part is important. Now while car is less than, sorry, greater than 0, I'll keep on doing this. Again, that is useful if I take something in both. So I'll have something like this. If set3 dot contains I, then both dot add I. And now at the end we will say if car is greater than 0, then from that both we will basically keep on fetching. We have already seen it should have the required number of elements. We are doing the best effort over here. After that the remaining should be present over there. So for we can again start from 0 So a left dot add only one of them, that is both dot get y, and I'll add this in the right as well. Let this in the right as well. Done. And after this you will just do car minus minus. Come out and you have to print, I think, L and R in the two lines. So less than 2 into k if I'm not wrong. pw.print, this is the printing statement. Whatever is in a left. Okay, it can actually be done in this way: for int y in a of left. Yeah, just put, okay, y is defined above, so z, and then z plus space, and then print a line, and then copy paste it for the right logic as well. So this one will be a right. Yeah, this should be working. Looks like for multitasking my laptop is slightly, Mac is slightly surrendering. That works for now. Okay, a lot of ones is not a good sign. A left, two into k. I think there I was wrong. It should be 2 into k. Now let us see. One one three three 2244 1133 2244 looks like it is correct. 1111, is that correct? Over here it did 1111. That does not look correct to me, because one is present only in the left half, one is present in the right half, so should have contained both. So one should not be present in the dev dot get. Okay, I seem to have missed this y plus plus. Yeah, now it looks fine. Error, interesting. Index out of bounds. Okay, here something was wrong. 1 2 3 4 1 2 3 4. Interesting. Car starts at 2k, nothing wrong with that. Car greater than 0 is also fine. Now I'm thinking, because it will reduce in steps of 2 only, right? 2k integers, right? Okay, let me read it once. 1 in line 458. Sorry, check index 398. Both dot get y. In both it should be there. N to 2n minus 1. 1 2 3 4 1 2 3 4. So in both only everything should be there. Set to okay, so let me print it to detect the mistake. Left plus I. Over here I'll print right, and over here I'll print both. Whether I'm adding right in the right way, that I'm going to check, and I'm going to run it only for that particular case which has malfunctioned. Okay, in both they have all gone, so that is fine. But why not 4? 4 should have also gone, right? 1 2 3 4 1 2 3 4. Are we missing it somewhere? Up to n minus 1 I'm doing, from n to n minus 1 I'm doing. So ideally both 4 should have also come. Okay, I'm missing that over here. That is bad. There's an equal to, and now it should be correct. Now let me. Okay, so pretty small case. Yeah. Now it looks correct. 1 1 3 3 2 2 4 4. No complaints now. I think we can go for the submission. Q. Cool. For the next two problems, I'll actually show you the solutions which I've already coded during the contest. So these are the two. So let's get started with the first one. I mean, these are from the div 1 thing. In the div 2, these are present as C and D. In the div 1, these are A and B. So let's get started with problem A, which I took around 11 minutes 51 seconds to give my first answer, and then there was a small glitch over there for which I took extra 5 minutes. So 16 minutes there. A bit of long time, I'd say. It should have happened quicker. Okay. Alice and Bob play yet another game on an array A of size n. Alice starts with an empty array C. Both are playing. It's a game theory kind of a problem. So Alice is going to pick up one element from the array. Bob is going to pick up another element. Then Alice, then Bob. In this way, it will continue. So you have an array. First, Alice will pick anything that she wants. Then Bob picks anything that he wants. Then Alice picks something. Then Bob picks something. Then Alice picks something. Then Bob picks something. There are even number of elements. So each will pick half of the elements. Great. Next, there is something like this MEX. You might have already faced it a lot in previous contests. And there was a video I made on a different problem of MEX. So it is the smallest non-negative integer which does not occur in the array. Now, MEX of this thing is 0. If 0 is not present, 0 will be the answer. If 0 is present, 1 is present, but 2 is not present, then 2 is the answer. 0, 1, 2, 3 are present, 4 is not present, so 4 is the answer. So the first whole number that is not present in the array, that is the answer. Now, Alice wants to minimize the MEX of her array, and Bob's wants to maximize the MEX of Alice's array. So whatever Alice gets, Alice will get some elements. Alice will get some elements AI, AI1, AI2, dot dot dot, AI n by 2, is it? Okay, n is odd, I think. I mean, n can be odd. Fine, no worries about that. Odd means Alice gets an extra turn. So n by 2, something like this. Okay. Now, Alice gets these. They will have some MEX. Alice wants to maximize this MEX, and Bob wants to minimize this MEX. What is the meaning of this? Maximizing MEX means accommodating as many numbers, accommodating everything under MEX, which means accommodating more number of numbers from the beginning. So if your MEX is 4 versus if your MEX is 14, 4 means 1 to 0, 1 to 3 are present. After that, 4 is not present. 14 means up to 13 everything is present. So Alice wants to take the best elements in such a way that Bob cannot. I mean, basically the MEX will be as high as possible. Bob will try the opposite. Bob will basically try to take the elements in such a way that Alice cannot keep a very high MEX. The MEX will be low. Mex we can say. Yeah. Okay. Now how can we solve this? For any kind of this kind of thing, you have to think from both the perspectives. What's the winning situation? What is that scenario? So let's say if I have something like your one example 0011, there is no competition over here because Alice picks the 0 and then whatever Bob picks. Bob can pick the 0 or pick the 1. Now which one will Bob pick? Why should Bob pick the 0? If Bob picks the 0, let's say here I'm writing Alice, here I'm writing Bob. If Bob picks the 0, there is no reason of picking 0 because 0 has already been taken by Alice. So now the MEX of the array will never be 0. So if Bob takes the 0, there is nothing that Alice is going to lose. So Bob can focus on the 1. But why that will not matter is because Alice has another 1 to take. So Alice can take this 1 over here. And then Bob can pick the other one, which means that Alice has 0 and 1, which means the MEX will be 2. Anyway, the MEX would be 2. MEX cannot be better than, or MEX cannot be greater than 2 because 2 is not present in the array. But this was a strategy. You saw that Bob has a greater incentive of picking what you have not yet picked, what Alice has not yet picked. Now, if I think in a different way, let's say only a single 1 was there. Something like 0, there can be plenty zeros. There is only one 1, and then there are plenty 2's once again. Now, what will Alice do? What will Bob do? If Alice picks up 0, Bob will immediately pick up 1, and that's it. MEX will become 1 because no more 1 is present, so Alice will not get a 1. After this, whatever happens, MEX will be 1. On the other hand, if Alice, let's say, picks up 1, then if Alice picks up 1, then Bob can pick up something like this 0, but that will not matter because Alice can pick up another 0. There are so many zeros. Then Bob can target the 2, but Alice can pick up a 2, right? So MEX in this case is going to be 3. So Bob will try this one, and Alice cannot prevent it. Sorry, Alice can prevent it. Alice can prevent it because Alice can start with a 1. So if Alice starts with a 1, then Bob cannot do anything. Bob can't trap at the 0, 1 or 2, either of them. So the MEX will be 3. If the situation was different, so here what we have seen that only a single value had frequency 1. So if any element has frequency 1, if any x has frequency 1, if any x has frequency 0, then what do we know? Definitely that can become the MEX. Then that x can become the MEX. X can be the MEX, nobody can stop. Can be MEX. Bob will try for a better MEX, for a smaller MEX. That's it. Now, if some x has frequency 1, then Bob can try to take this. Bob can try to take this. And what will Alice do? Alice will try to take it first. Only one of them can take it. Since frequency is only 1, it is present only once. So only one of them can take it. Bob will say, okay, if I take it, that it becomes the MEX. If Alice takes it, then that is not no longer the MEX. So Alice can also try. Alice can pick this at the beginning. Pick at the beginning. Now, if Alice can pick it, Alice should pick it. If there are multiple elements, what should Alice do? If there are multiple elements with frequency 1, let's say 3 and then 5 and then 7, something like that, then Alice can basically pick up, Alice can pick up any one of them to secure that. If Alice picks up the 5, Bob can pick up this 3, so MEX becomes 3. So Alice definitely wants to secure the smaller ones first. So Alice can say, okay, I'll pick up this 3 first. So Alice takes this 3, right? And then Bob can say, okay, I'll not waste my time on the other things. Maybe your 1 is present twice, 2 is present twice, 0 is present twice, 4 is present thrice, or whatever. Bob will not waste any time. Bob will just pick this 5. This is Bob. Bob picks this 5, so automatically Alice cannot secure the 5. All the others, notice this, all the others which are present twice, If some element is present twice, then what can, if x is present twice, let's say, or frequency is greater than twice, greater than 2, then Bob gains nothing by putting that. Why? Because in some move, let's say Bob puts the x, in the next move, Alice can take the other x, neutralized, no gain at all from this particular thing. So we can just ignore them. If frequency is greater than 2, Bob has no intention, Bob cannot do anything by choosing that. You can just ignore that. Okay, that is secured. That is secured. Whenever they take it, that is secured. So x is fine, right? Because in any move, if Bob picks it, next step Alice will pick it. So how Bob will actually try to threaten Alice is by picking the ones with the frequency equal to 1. Only these ones are the most important. And if you have multiple such elements like this, if you have multiple such elements 3, 5 and 7, Alice can only protect one of them. So Bob will pick up the next one. And in between these elements, from 0 up to that element, if any element is missing, that automatically becomes the MEX. No questions about that. So that is the basic logic. So if you have some complicated thing, something like this, let's say you have 0, 0, 1, 2, 2, 3, 3, 4, 5, 5, 6, something like this. Whatever they pick up, first of all, Alice will try to secure this. If Alice doesn't secure this, then Bob will pick it up, answer will be 1. The MEX will be 1. So Alice will try to secure this. This is definitely Alice's first move. Whatever is the one with frequency 1, whatever is the element with frequency 1 from the beginning, Alice will first secure that. Then Bob can actually pick up, Bob will actually try to secure this one, this 4. But you can already, okay, I may have missed something. Yeah, Bob will actually pick up this one, let's say 4. Bob will say, okay, this is the answer. Now whatever they pick up after this, 4 is going to be the answer. So the MEX is going to be 4. That is the best. Now if it is slightly different, let's say the 2 3s are not there. Let's say the 2 3s are not there. Yeah. So then Alice will pick up this one, A, to secure it, and then Bob can definitely pick up this one, but you should be careful that this 3 is missing over here, means this 3 already has become the MEX. Before this, Alice has secured everything. Before this, there is only one element with frequency 1 which Alice has secured. If there are multiple elements, then Alice would pick up one, Bob will pick up the another, that another thing will become the MEX. Each will try to pick up the smallest one so that the smallest one is protected. That is the logic. So this particular algorithm you have to apply. Let us look at the code. This is it is totally a game theory question. So the code also works that way. There was a small mistake I made, which was basically I assumed that 0 is the first thing that Alice is picking. That was my mistake in the first iteration, but then I corrected it. So this was how I corrected it. X I stored. So basically I am storing the frequency over here in this map. Okay, I am iterating through the array and I am storing the frequency of every element. Then from the beginning till the end, from 0 to n, I am storing. Why up to n? Because the MEX will be at max n. So up to n I am interested. So up to n I am storing which is the first element that has frequency 1, if any. Which is the first element that has frequency 1, that is x. So I'm storing that in x. So that particular I am storing that in x. And then I'm coming out of this loop. And then I'm going from 0 to n. And I'm saying, okay, is 0 not present? If 0 is not present, directly that is the MEX. Right from the beginning, if an element is not present, then that becomes the MEX. If an element is present only once, then if that is the first such element, then Alice will pick it up. If that is the first such element, Alice picks it up and continue. If that is not the first such element, if I equal to x is not correct, then that is your MEX. Bob picks it up, that is the MEX, that is the answer. Got it? So simple, big O n, time complexity. This was very clear. I mean, this was a game theory question. and the constraints made it clear that we don't have any quadratic kind of thing coming into the picture. Yeah, and this somehow, this particular thing that AI goes from 0 to n gives us an impression that okay, if we look at elements one by one from 0 to n, that approach works. We have seen that also for I think problem A or problem B as well, right? Um, this was bridges. So problem B we have seen. For problem B we have also seen such kind of a thing, that all the elements are from 1 to n. So from 1 to n you can directly apply that loop. From 1 to n do this kind of thing. Okay, that's it. Now the last problem, which is definitely the best out of these four. There slightly a good algorithm has been used. So I'll talk about my solution and maybe slightly brainstorm about what other possibilities were there. Okay, so first palindrome has been defined. We all know what is a palindrome. We have to say ft equals to the sum of all values of k such that string t is k good. And this k good is a bit interesting definition. K good means there exists at least one substring of length k which is not a palindrome. So if at least one such substring is there of length k which is not a palindrome, then we say that is k good. Okay, not the other way around, that if you find a palindrome of length k, then that is not k good. No. If any one you find which is not a palindrome, a k length substring which is not a palindrome, then that string is k good. Okay, now ft denotes the sum of all the values of k such that the string is k good, which means if a string let's say s is something like, let's say 2 good, 3 good, and let's say 5 good, then the answer will be, hypothetically, okay, the answer will be then 2 plus 3 plus 5 equal to 10. Okay, whatever k goods are there, the sum of those values of k. Okay, next, you are given one string and now you have to say for L to R, that particular substring, what is the value of f of SL to SR. Very good problem in terms of the algorithm that is used. So first thing is palindromic substring. First let's understand the problem. So if we have something like this, PQPCC, or let's say AAAB, AAAB. So if I talk about this whole thing, 1 to 4, okay, L equal to 1 to R equal to 4, I can say that only one length ones, A, and B, only the one length, single length ones are palindrome. Rest anything, any length if you say, let's say len equal to 2. Len equal to 2, AB is not a palindrome. So it is 2 good. Len equal to 3, AAB is not a palindrome. So it is 3 good. Len equal to 4, AAB is not a palindrome. So it is 4 good. And hence we will add it. Len equal to 1, they are all palindromes. So we don't have anything coming out of there. Only non-palindromes we will try to look at. So adding these we get 5 plus 4, 9. Let us see. If we have, yeah, for 1, 4, the answer is 9. Right. Now, how do we solve it? For this, realize this, that your L to R, it can be even or can be odd, and so are their substrings. Now, any L to R that is given, for the time being, let's imagine that that is odd. So you have some, let's say 5 characters or 7 characters, let's say. In big O, one time if you have to find out whether it is a palindromic substring or not, one algorithm that directly comes to the picture is Manacher's algorithm. Manacher's algorithm or Manacher algorithm. This algorithm helps us find out the maximum length of palindrome around any center. Maximum length of palindrome around any center. Alright, now let us see how Bannister's algorithm works. This is one thing. Apart from telling us what is the maximum length of palindromic substring of a string, palindromic substring of a string, this tells us that what is the maximum length of palindrome around any center. This is a big thing. So if for an example, basically for an example, how does it do it? Something like this. Let's say BAAB, BAAB. It writes in this way, this entire thing, B slash A slash B slash A, sorry, BAAB, BAAB, BAAB. And now, okay, you have something over there as well. For each of them, it will tell, okay, how many characters to the left are matching with how many characters to the right. So for this B, it will say only one character. So the answer will be 1, something like this. For this slash, this B is not matching with A, so this will give a 0. For this slash, this A is matching with this A, this B is matching with this B, so this will give a 4 actually, because 4 length, it's a total of 4 length that is matching. So somehow, I mean, you can look up the implementation actually, but these are the values that it gives. This A will basically give you again 1, and this A gives you similarly, so only 1, and this slash gives you again nothing, these are not matching, so 0, and so on. Let me do this, complete this. So for B it will be 1, it itself, B itself, and actually it will mark these two particular boundaries, they are matching, so it will mark it as 1. But anyway, whichever way you look at it, and this particular line will tell me everything in the left is matching with everything in the right, so this will give an 8. And now it will be something like this: 101 4101. Yeah. Now, so this tells me this particular thing, if I call it, let's say L, basically L of I tells me that what is the longest palindrome centered at I. The length of the longest palindrome centered at I. Great. Now, how do I utilize this to solve my problem? If you do this manager's algorithm one run, it will give you these information, and this manager's algorithm will give you this information for all the places. I'm writing managers. Manager's algorithm will give you all the places, and then big O n time, right? And big O n time, where n is the length of the string. This is a very good thing because you have only one string. So for one string, you will do this once, and then you can find out so many, you can answer so many queries related to palindromic substrings. Now, what next? If at some position, let's say, I have some string, let's say, of 5 characters. Now, these 5 characters will basically occupy some places like this. So I can do the mapping easily. I can quickly do a mapping, that kind of mapping I've done, that okay, I can do that mapping internally. But basically, okay, there will be some mapping, and I'll come to know that what this guy is telling me. If this guy tells me something like greater than equal to 5, then it is not 5 good. I can say that okay, this itself is a palindrome. Mind you, it will tell you with respect to the entire string. So it may not be 5, it can be greater than 5, it can be 7, 9, and many other things. So the moment it tells me something like this, I know okay, it is a palindrome. What next? Now, that means it is not 5 good. That means it is not 5 good. Not 5 good. Can it be 3 good? Yes. If it is something like this, let's say AAB, AA, then it is 3 good, and yeah, it is 3 good. Then why? Because AAB is not a palindrome itself. So length 3 is not going to get protected by this. Which means, if you think a bit, probably it will turn out that if there is any difference in an element, okay, there is one different occasion, however, this thing, B, A, B, A, B. If you have this kind of situation, then again you can say the same thing. That, okay, whichever 3 length you pick, this 3 length, this 3 length, this 3 length, they are all palindromes. So this is not 3 good, which means you need a way to find whether it is going to be 3 good or not. For 7 length also, you need to find whether it is 5 good and 3 good or not. Now, if you think a bit, you will see that, okay, it is this alternating pattern that we need. If we don't have this alternating pattern, somewhere or the other, it will not obey. For example, let's say you have something like this, AAB, AA. If you have a bigger one, let's say AA, BC, BAA. Or if you want me, I can just restrict to B. You pick up anything that does not have the alternating trend. This is 7, and this is 7. I mean, this is a palindrome. Let's say you detect that this is a palindrome. Now, on top of this, you need to detect whether length 5 ones are all palindromes or not. You can see the alternating trend is not there, so it is easy to find out an example. Okay, this is not a palindrome. Now, for length 3 also, it is not that difficult. Wherever that intersection is happening, take something over there. Not a palindrome. So, if you think of it, you will find out that, okay, if first thing is, if it is itself not a palindrome, so for odd length ones, you can say whether the biggest length is a palindrome or not. The whole thing is a palindrome or not. If yes, then you need to ask, okay, is it having all equal otherwise alternating trend? All equal otherwise alternating trend? If yes, then all odd lengths are palindromes. All odd lengths are palindromes. And if no, then before that n, only one is that odd length which is a palindrome. Other than that, none of them will have all palindromes. So only one length palindromes. Only one length palindromes which are smaller. If the whole thing is not a palindrome, that means for any odd length it is not a palindrome. Any odd length, it is not a palindrome. Any odd length, not a palindrome. The question is not about whether you can get a palindrome or not. The question is whether all strings of that length will be palindrome or not. So these are the two conditions. First of all, the whole thing has to be a palindrome, otherwise forget it. Okay, any odd length except 1. Except 1 is important. Except 1, and here also 1. One length is always a palindrome. And this is the case where all the odd lengths are palindrome. This is another deciding factor. All are equal or alternating. How do we find whether all are equal or alternating? My procedure was something like this, that around this guy, if this guy says that, okay, this particular part is a palindrome, and this guy also says that this particular part is a palindrome, then you can equate something. So basically something like this. This is the center. And beside this you have two other characters. This is a palindrome. Okay. Now, if this guy says that from the left boundary, this is the center of a palindrome. This is the center of a palindrome to some place. As well as this guy says the same thing, that this is the center of a palindrome from the right boundary, if both are palindrome, then I know that this condition is obeyed. You can think a bit, you can have actually other easier ways of finding it out, but since I have the manager's thing, so I did not mind finding it out. So what I basically did was basically this L of this center, you can do those translations basically, L of this center and then L of the left of that center and L of the right of that center. These are the three things that will tell me. L of the center will tell me this thing, whether it's whole palindrome or not. If no, then directly go and say only one is the thing. And if all the three are true, then you come over here. Otherwise, in between, you enter over there. Yeah. So these are the possibilities. So just from the manager's algorithm, from the output of the manager's algorithm, from the results, we can obtain those answers. So in some other session, maybe I can talk in detail about manager's algorithm, how it actually works, why it actually works, etc. That's a slightly difficult thing, but you can use manager's algorithm in this way. One of my all-time favorite algorithms, the manager algorithm. You can utilize in this way. Now the even length ones, maybe you can brainstorm a bit, but for the even length ones, in short, if I have to put it, you will see 7, 8. If this is a palindrome, that means if you place a mirror, they will all match. Now, if any element is different, let's say if you have an A over here and let's say if you have a B over here, then 2 length will never be a palindrome. Why? Because this thing, 2 length will not allow to be a palindrome. 4 length again will not allow to be a palindrome. 6 length again will not allow. Why? Because we will start from something like this. Either we'll end there or we will start there. Anyway, we will definitely have that. So we will keep that. So why that 6 will not be? Because you know that if that is B, then this will be B and this will be A. So if I do something like this from here to here, then, or I can do something like this from here to here in case of 6. Okay, no, that is a palindrome. I can do something from here to here. 1, 2, 3, 4, 5, 6. So center is here. Yeah, A and B are mismatching. So you can actually do a lot of examples and actually convince yourself that for even, these are the possibilities. For even substrings, oops, was I not showing that? From a long time maybe. Okay, so maybe I'll quickly just throw light on this. If it is an odd length palindrome, then I'll check whether the whole thing is a palindrome or not from the manager's algorithm, and then I will come to, if it is yes, if it is a palindrome, then only I am concerned about the smaller odd lengths. I'll consider this particular part. Otherwise, I'll just say only one is going to be a palindrome. Length 1 is going to give you a palindrome, otherwise not. If I find all equal or alternating patterns, like this thing, BA, BAB, or this thing, A, BB, okay, this is not, so this kind of a thing, or maybe all are A's or all are B's, then only I will get this kind of thing, that all odd lengths are palindromes. And this thing I can check using just these two values. So I will check LC, L of the left of C and L of the right of C, and just looking at those values, if they are the maximum possible, then I know that it is a perfect palindrome. If it is a perfect kind of a palindrome, then I know that okay, all the odd lengths are palindromes, otherwise not. Otherwise only one length. One length is definitely something that you have to keep in mind. This was something that I had skipped, due to which I had to struggle for 47 minutes. Over here, this only one I had skipped. Here I had taken the one, everywhere else I had taken the one, but here I had skipped it, only one. And as a result, I actually had to submit it once again after 47 minutes. For the even length ones, you can actually see if all are equal, then only every even length substring is going to be a palindrome. If there is any difference, any place where the two successive characters are different, that automatically becomes the reason why all even length substrings not equal to the entire length is going to be a non-palindrome. That also you can figure out from these two values only. You can just read from here whether at these positions or maybe at these centers whether it's a palindrome or not. At these centers whether it's a palindrome. This center whether it's a center of a palindrome from the left boundary or not, up to here, and whether this particular place will be a center from the right boundary or not. You can figure it out. Okay, this center I've drawn in a different way. So yeah, ideally, yeah, you have to pick up from this center and this center. Yeah. This center and this center. Yeah. So whether this part is a palindrome or not, and whether this part is a palindrome or not. So for even, you can just check those things. For the even, the chart will look something like this. That if the whole thing is a palindrome, then only look further. If not a palindrome, forget. Then none. So no even number length substring is always a palindrome. If yes, then you have to check, okay, then the previous one and the next one. So at that previous boundary and the next boundary, whether over there they are palindromes or not. So Brave and next, whether they are also, centers of palindromes or not. If yes, then all are going to be palindromes. All. And if no, then only that's substring, only that length, only that particular length which you are dealing with. These are the possibilities. So let us see how the implementation goes. Yeah. So here I found out the longest palindromic substring. I have taken the code from the internet. I did not strain my mind. That's how most competitive programmers would do. They would take these implemented algorithms from the internet and they would use it. So I've taken this, I've solved, basically I've fetched this longest palindromic substring. And then what I've done is, for every query, L and R, I'm basically saying, okay, if L is equal to R, then definitely nothing to see, leave that as 0. Otherwise, these are my converted things to that L array. In that L array, that is a slightly expanded form, we have extra pillars in between according to manager's algorithm. So I'm forming this converted length and converted left and converted right. Now my length of the actual substring that I've been asked is basically R minus L plus 1, right? L to R, that is R minus L plus 1. Now I'm checking whether my center is even or not. This is just a way of making my understanding easier and simpler. So if it is even, then the main task is even. So I'm basically saying, okay, if yourself you are not a palindrome, this is the detection. If P center itself is less than len, then even is, then it is K good for all the events, right? We have to count it as a violation for all the events. So sum of even up to len. This is a function that I implemented. Sum of even, basically sum of all the even numbers up to n. You can derive it mathematically. Similarly, sum of odds is basically sum of all numbers up to n minus sum of all even numbers up to n. I could have called this function over here, but anyway, same thing. Next, what did I do? If it is less than len, that means I am over here in the graph. None. So it is K good for everything. Palindrome for nothing. Now, if this is equal to len, that means I proceeded in the left side. Now there is a condition previous and next. So previous and next, if either of them is violating, if either of them is less than len minus 2, P center minus 2 and P center plus 2, if either of them is less than len minus 2, I will say, okay, then take only up to len minus 2. So len itself is valid, but len minus 2 and all the previous even numbers, for them you will not get all palindromes. So I'm going to take only len, I'm going to relieve only len, and the rest I'm going to account for in the k good, if it is no. Now, if it is even not that, then I will say okay, then everything is good, you don't have to take anything. So if this was equal to len, if they were equal to len minus 2, that means everywhere you have palindromes. So you will have even equal to 0. Same condition I pasted over here as well. If the entire thing is odd, then you are coming into this else. At the end I am saying okay, then just one step behind from the center and look at that even thing. And now we are checking only that that thing whether everything is equal or not. If everything is equal, take that. If everything is not equal, no chance. So this is just a way. You could have used some prefix structure also to say whether everything is equal from the beginning to the end of the substring. Yeah. Okay. What else? Now the odd part. The odd part which I have found over here. Whole palin and equal alternative. So let us look at it. If the whole substring is odd, then these are the three conditions. First condition, if the whole thing is palindrome, let's say not a palindrome, then 1 is the only thing you are going to relieve. So let's look back. If the whole thing is not a palindrome, then all the odd numbers except 1. Sum of all the odd numbers except 1. That is the right part of that flowchart. Now, the next part, that is this part. If all are equal, alternate, if that is not the case, how am I detecting that? Center minus 1, center plus 1, those two particular values. So then only one length position, only one length palindrome, which basically means you have to count everything up to len minus 2. Up to len minus 2, you have to count everything. So that's exactly what I have done. If they are not palindromes before and after, then I'll count everything up to len minus 2 except 1. And the final thing is all are good, odd equal to 0. So this is that case, all odd length palindromes. This is that case. Yeah, all odd equal to 0. This same thing I have written here, the last two conditions, that left and right, they should match. This indicates that all the elements are equal, they are happy, or they are alternating, either of them. This particular thing guarantees that. You can also use hashes, etc., or other kinds of techniques to find that out, whether you have the alternating trend or not. And then finally you say, okay, if that trend is not there, then odd equal to 0. At the end of each of these, you will write even plus odd as your answer. That's it. Slightly tricky kind of a question, slightly complicated looking, but slightly cases as well, but it uses such a good algorithm. And then you just need conversions to that data structure, which is an easy thing, fairly easy thing. One suggestion is something like this. So send it for some string and then print that pi, understand in what way that is returning. So because you are going to use that. So that is something that I did during the program. Yeah, it would I could have submitted it 47 minutes before, as I showed you. If I show you my wrong submission, you will see only that -1 was missing. So if I show you my wrong submission, you see that in the odd here I had mentioned the -1. In this particular odd thing, I forgot mentioning that -1, and that actually cost me so much of my rating. But it happens. This is what competitive programming is all about. Here, had I put that -1, that is the only difference. That is the only diff between my two answers. So anyway, that's it. Could we have done it differently? Yes, there are other ways. You can definitely try. You can maintain some kind of a count that will tell you up to a particular point what is the kind of what is the kind of thing. But remember, for a certain element, for a certain position, you can't store more than log n kind of information. You cannot store a lot of information. You can store 20-30 units of information, an array of 20-30 different things for a certain location. You can store that, Would you can't store that, okay, can I have 1 length, can I have 3 length, can I have 5 length, and so on. You can't store all those information because it's going to overshoot the. Somewhere I feel it is necessary to know whether it is a palindrome at a certain center or not. And for that, this particular algorithm, manager algorithm, is very efficient. So that's why I use manager algorithm. You can definitely try out your other algorithms. You can try out maybe thinking a bit on Rabin-Karp or KMP. I haven't put such a deep thought into them. You can put some thought and see if you can solve using that. And similarly, C problem is on graphs. This looked on DP to me when I was solving it yesterday in the contest. In some separate session, maybe I can discuss it. Yeah, DP and a bit of combinatorics. Take a look at it. Yeah. So I hope you enjoyed the session. This was a slightly difficult contest, slightly mathematical contest. So sometimes you should upsolve these problems so that you can actually crack all kinds of problems in all kinds of contests. So okay, see you in the next contest, see you in the next videos. Take care, keep coding. Bye.